Yeah, so this is the way I could do that. Then my computer recorded. You know how I say?
Yeah.
Yeah, so you can go ahead. Could people on the ruins hear us? Hello?
Thank you.
Oh, no. Hi. Hello?
No, I don't think so. Can you hear us?
We can hear you. Can you hear us?
Okay, sounds great. Then let's start.
The root. Okay, hello everyone. My name is Sanchit. Here. And this is my update point spread function reconstruction for Keck. This was part of my thesis project that I worked on for the last 3 years. And the idea here is to validate an on-axis point spread function reconstruction, specifically for the NERC2 imager. NERC2 is the near-infrared camera on Keck, and it's basically their workhorse imager for adaptive optics. So that's what you'd use. That's what the Galactic Center uses. This is actually a cool photo of the Galactic Center observing simultaneously. So both LGS stars are pointed in the same direction. So this is pretty basic, but here's your typical AO system, missing the DM actually, which would go somewhere in this part of the wavefront. But what an AO system allows you to do is focus your Gaussian into a really sharp image. And the reason why I like this particular image is because what I'm going to talk about, we're trying to reconstruct the PSF from first principles without using the science image. So what I'm trying to do is basically predict what the PSF looks like on this image without using that image specifically in and of itself. And so what we need to know is pretty much everything that happens along this path. So we need some measure of the atmospheric turbulence. We need some measure of the quality of the telescope primary and any subsequent optics in that optical chain. And so this is the Galactic Center with and without PSF, with and without adaptive optics, sorry. This is a significantly old image. Now with some of the new infrared images, the infrared tip tilt correction, you can actually start to see PSF rings around individual stars too, which is part of this upgrade that I'll talk about. So this is kind of something people here would probably know very well about, but your PSF depends on your aperture. And so if you have a circular aperture, you have an area ring, that is the Keck aperture, giving you, that is a perfect diffraction pattern. But the critical thing here for the purpose of this talk is the observed PSF is a Fourier transform of the aperture function. Like in a perfect world, you would just get a perfect PSF. But computationally speaking, if you want to do this exercise where you're trying to predict a PSF based on your optical chain of what devices your beam goes through, in theory, what you could do is you can convolve these PSFs, but that comes with its own issues. It is computationally much faster to work in the Fourier space because then you're multiplying transfer functions instead of doing multiple convolutions. That has its own problems, but it is still better than the alternative. So now I'll briefly address what we're trying to do as compared to something people would do classically. So when we started this project, my specific objective was to basically solve this kind of a problem where you have a PSF from a quasar, and then what you want to do is reconstruct the PSF and subtract it out. And what we want to observe is the quasar host galaxy in the vicinity of the PSF. So this is not novel in and of itself. People have done this before. So the top figure is using Hubble, and the PSF was reconstructed using Tiny Tim. And people have seen host galaxies around these quasars. The bottom figure is actually from 2006 from Olivier's paper. And these are like using on-ground imaging. But the issues here are basically what we want to do is do this exercise, but instead of fitting a PSF, you want to try to reconstruct a PSF. So there are a lot of things you can do with PSFs, and it's often confusing what they are. So this is kind of a map to situate us and in all the sorts of PSF techniques. So basically, when we talk of classic, when you want to fit stars in the galactic center, that's usually in this realm. We're using something like Dalphot or Sextractor. You're doing basically a fitting on a science image. You're fitting the PSF, you're extracting it, and then you're doing your astrometry. You can deconvolve, and this comes with its own issues. It's basically what you're trying to do is, well, the PSF is a Fourier transform of the aperture. Can you do the inverse transform somehow and then deconvolve that out? That kind of an approach. PSF learning, this is new. So this is using something like the machine learning kind of approach. This is what I'm actually starting to do now for phase retrieval. So that's where we are. But where we sit right now and what I'll be talking about is this approach here, is a PSF reconstruction. And the goal here is basically to take all the information you can get about your atmosphere from any auxiliary sources, get all the information about your static errors in your system, take your actual AO telemetry data and use that data to reconstruct the best PSF you can. And this is basically what I'll be talking about is a post-processing technique. Like, we're not changing the AO system in any way live. We're taking all the data it provides us, we're taking the science image, and then we're doing all these calculations after the fact. People simulate PSFs as well, but not really going to talk much about that here. So what are some of the science cases we're trying to address? So these science cases are what Kappa was built to target. So Kappa is the Keck All-Sky Precision Adaptive Optics Upgrade. And I'll speak about that towards the end of the talk just briefly. But the four science cases they were trying to target are basically your exoplanets and your sort of protoplanetary disks, resolving those around a host star, better astrometry at the galactic center. In this case, the galactic center is a very special case because Keck spends a lot of time looking at the galactic center. But galactic center is also a very crowded field. So that is where your actual field of view aberrations become important. Your individual PSFs sitting on top of each other, those kinds of effects become really important. So better PSF there does give you like significantly better astrometry, photometry, which is really important because the stellar motion basically drives their gravity models. And so it's really important for them to have really good PSFs. Galaxy evolution is the case I described where you're looking at quasars and you're trying to subtract the quasar PSF to look at the host galaxies. And then dark matter, this is a pretty unique case, but basically you're looking at gravitational lensing around, again, some foreground galaxy. And knowledge of the PSF gives you better gravitational lensing constructions, and that gives you better constraints on dark matter halos and how matter might be distributed around basically the foreground galaxy that's acting as the lens. So what do we need to forward model this PSF? What I'll be using is this code called P3 or Prime. It's now also called TipTop. It can do a whole lot of different things, and it can get confusing between a lot of different versions, which is like a very good advert for like having your GitHub together and keeping everything organized. But primarily what Prime can do is it can reconstruct this on-axis PSF. And by reconstruct, we mean we take all this information, we don't look at the science image, and we construct a model that can construct a PSF. It can also do this Fourier model, which can then be fit to the images. So it can do both of the things, and that's what I'm going to do. But this fitting is done in Fourier space. So instead of fitting like your actual PSF on your actual image and then using like your Strehl and full width half max as the parameters, it's actually going to transform the thing into transfer functions. And then the parameters are going to be in this Fourier space. They're going to be like your gains. They're going to be like what are your frequencies you're trying to fit, something like that. And that will give us an optimal PSF. For the forward model, for reconstructing the PSF, we need data. So some of this data is the AO telemetry files. And then your data from mass and dim instruments. So these are the instruments that profile the atmospheric turbulence on Mauna Kea. The calibrations of the static aberrations. So this is basically running phase retrieval on just downstream from your AO system to get only your static errors. So this is done during daytime. There's no atmosphere involved in this process. So these are what we call static maps. And then we reconstruct a PSF based on these inputs. There are a large number of other inputs I'm not talking about, and that's primarily because these dominate our errors right now, and these are the most important ones we're trying to sort out. And then what I'm going to do is basically we're going to compare the performance of this fitted Fourier model. We're going to fit this Fourier model, and then we're going to compare it to this forward model PSF. So what are the forward model components? So there's two parts to the forward model. One, you have the static part of the telescope, which is not changing on a per observation basis, or you have an assumption that it's not changing on a per observation basis. So there's your pupil map, which is the most reliable and like the biggest contributor to your PSF. But then what we have are these phase retrieval maps that are obtained on the AO bench using this basically a single laser fiber through the AO system onto your science detector. And you basically run phase retrieval on them to get what are your deformations on your non-common paths, so your non-common path aberration maps. And we combine these to get basically our static optical transfer function. That'll give us a static only PSF. Now, note of caution about these NCPA maps. We only have a limited number of NCPA maps. So for example, I was free to choose data for like 6-7 years for this project, but we had roughly 1 or 2 NCPA maps per year. And so we don't, yes.
What's the NCPA?
So NCPA is the non-common path aberration. So basically it's the difference between what aberrations your deformable mirrors can see and correct versus what is downstream of basically your dichroic when it goes into the science instrument. And there are some errors which the deformable mirror just can't see or correct. You assume, but there's an assumption that those errors are static, which is why this is in the static part. And it's a reasonable assumption because they're mostly going to be optics inside the instrument and whatnot. We don't know, though, how much these change. Also, we're running phase retrieval to like get these errors. So if you've done phase retrieval, you know how tricky it is, and it is really difficult to get like a very reliable map. But we work with what we have. So the data, for example, that I use for these reconstructions, it was somewhere like 3 to 4 months after these NCPA maps were taken. So they were not exactly done at the same time. And this is partly the challenge of this technique is it has so many inputs that are demanding on the observatory that we can't just have everything for all data sets. So we actually need some targeted effort to do this. Yes.
What are you using to probe for the NCPA masks?
Sorry?
What are you using to probe for the NCPA masks on
Probe for the NCPA masks, but then like how do we obtain it?
Yeah.
So basically what you do is you have a single laser fiber. And then you basically point it down the path from the AO bench. So the AO bench, instead of seeing the image from your primary or whatever you get during daytime, you put a laser fiber through it. You know it's a point source, right? By design. And then you ask basically your AO system to correct it, and you're also imaging it on the science camera at the same time. And then based on your sort of best AO system corrections, you get like a science image. Right? And you assume your AO system's done the best it can do to correct. And your science image is still not perfect. So you then assume your aberrations are due to this path that your deformable mirror can't correct. So there's no atmospheric turbulence that can be there, right?
If it's on the AO bench, why isn't it done more often?
So because running this, like someone has to physically do this on the bench, you have to be in the dome. So you can only do this at daytime. You can only do this after the telescope's been released, and that's like a 2-3 hour window. So typically you would do this like on nights when either your AO system's not being used or like you basically have engineering nights, something like that, where you're not compromising someone's science. right? And the other thing is it's a personnel intensive thing. Like someone needs to be an expert on like running this and then resetting the AO bench back to like whatever the nominal was. So it's quite an operation to do this on the AO bench. So, and there are assumptions that go into like how good these maps are. Then there's a second part of the PSF, which is what we call the turbulent part. So this is the part that is changing kind of live as you're taking an image. And this is a difficult part to kind of nail down. So in this particular model that I'm working with, like you can have a lot of these different components you can take into account. This particular model is taking these four kinds of errors that can creep into your live measurement. So there's like AO, tip tilt, aliasing and fitting kind of are self-explanatory. What they are, tip tilt is basically what is your residual slope correction from your tip tilt corrections. And then the AO is basically taking into account anything from your wavefront sensing kind of errors, your noise errors and your wavefront sensing that propagate into your correction. That depends on like what kind of wavefront sensor it is and so on and so forth. So these are all combined to form this optical transfer function. It looks a little bit simplified. There are quite a few knobs in between these two layers. Like we have some gains we can tune, and tuning those is not trivial. Like you have to mess around with it a lot. That gives you one optical transfer function, and that gives you the only turbulent part of the PSF. So for example, if I just combine the results from these four power spectrum densities for a typical measurement, you can see this is what the PSF looks like. You can actually see it doesn't look hexagonal at all because there's no concept of the pupil in that PSF. You can do this exercise with like any power spectrum density. I will say that our dominant error right now is this tip tilt power spectrum density, which is basically low order corrections we are unable to do really well. And then the residuals from those tip tilt slope corrections that are basically the dominant error in like the PSF we're constructing right now. And these two then combine to give you a forward model PSF. Now I will say, because your left part is the turbulent part, so that's the part that's coming when you're taking the actual image, that is done on a per image basis. Typically, when you see like any galactic center kind of image, you see a stack, you see like several exposures stacked together. You have to do this exercise on a per exposure basis. Plus, a lot of these input files, like the telemetry files, for example, can be something like 300 to 400 megabytes per exposure. So if you have like 100 exposures, this is quickly becomes a data management problem on top of everything else. So that gives us one forward model PSF. And we can now compare kind of how well that does compared to a fitting approach. So a fitting approach is slightly more classical. Like I said, we're fitting in this Fourier space. So this is not like your classic fit the height of your PSF fit. This is fitting basically your spectrum in your frequency domain, spatial frequency domain, and trying to get the best PSF. So over here on the left, I have images. So this is actual data on sky. The first one is actually like one of the first images of the night, like kind of around twilight, to show you like the worst case performance almost. And on the right are these fitted PSFs using Prime, like the same code, but a different model. And then what I can do is I can compare the Strehl ratios for the actual image and the fitted image here. So that's shown here. And the other thing I can also compare are the full width half maxes. So these full width half maxes, you can make X and Y directions because the PSF doesn't have to be symmetric. And they show a reasonable agreement, but there's a caveat here that what we want to do in a lot of our science cases is we want to reconstruct a PSF specifically so we can do science just beyond the core, right? Like you don't really care about the core. In the quasar host galaxy, you want to subtract your core and look beyond that, so you want a good PSF. But these metrics are actually dominated by our core, like your Strehl, your full width half max, are mostly dominated by what your core is doing, how well your core is fitting. The other thing I will say is while these fits look really well and they perform really well, because these fits are in Fourier space, they have a number of parameters that are being fitted that are real. So one of these, for example, is the Fried parameter. And oftentimes, even when we get a good fit, we get unphysical parameter fitted quantity. So we would get a Fried parameter that's like 20 meters with a good fit. And it doesn't always make sense. What it's basically probably telling us is, yeah.
Sorry, what are the difference in the colors?
Oh, so the red and blue are basically our X components and Y. You can do a full width half max fit as like a sort of linear sliding Gaussian kind of thing.
You're not seeing a bias in X versus Y.
Not really. Also, this data size is a little bit small for this, but not immediately with this. Yeah. So what the unphysical Fried isn't telling us that the model is necessarily bad. What it's probably telling us is we have our sort of other parameters may be wrong, because the other parameters are these gains we put on these other power spectrum densities. And that's more likely the reason. If we tune those gains to be right, our Fried parameter is going to be back to track. So how do these compare to the forward model PSF? So this is again the fitted PSFs and the residuals. You can see there's some systematics here. The residuals are positive in the core. Then there's a negative bit where there's clearly over subtraction and there's under subtraction again. So it's very systematic, the kind of fitted PSFs we're getting. And if I compare this to the forward model PSF, now that kind of systematic goes away. It's a more kind of in many ways real looking PSF. So this here is a forward model PSF. And I'll remind you, like, this PSF has never seen the science image. Like we basically conjured it out of thin air. And you can see now it's still off, but it's no longer off in this weird symmetric systematic way. It actually captures a lot of the asymmetry of your telescope. Granted, it's not perfect, like those asymmetries aren't aligned. It's not because of a rotation angle effect. That's one of the first things I looked at. So it's actually producing a real PSF, which doesn't really care about your science image. And that is progress. So how do we quantify this performance in addition to your Strehl and full width half max, which are kind of similar? What we do is basically this fraction of variance unexplained, which is similar to your normalized mean squared error for a PSF. And what we find in this case, in the best PSF we can produce, this is about 7.5% for a 30-second exposure on sky. Now, for reference, the galactic center group, they can produce these FBUs to about 3% with fitting. So we're still like a factor of 2 off. But given the fact that, again, this has never seen the science image, like it is doing a pretty decent job. The other thing is we know there are systematics we are investigating that were incorrect as of writing this that need to be improved. And the other thing is we don't really know about this time drift factor of our NCPA map. So we know that our inputs are not all perfect, and we also don't really have a very good handle as of now of like how they drift with time. And so there's definitely like improvements to be made, but it is a promising result. So what is kappa and how this whole sort of approach fits in with this upcoming project? So this entire research was funded to work for kappa. So what is kappa? It's upgrading the single laser guide star, single conjugate adaptive optics to a 4 laser guide star system. The goal is to improve the Strehl, improve the sky coverage, and have accurate PSFs. How is kappa going to do that? So it's tied into like a massive hardware upgrade. So first of all, you go from 1 laser guide star to 4 laser guide stars. You have better anisoplanetism. So you basically get better PSFs. You have a new real-time controller and a new wavefront sensor camera. And that should give you basically a better Strehl. The sky coverage part actually is tied to this bit, which is now a near infrared tip tilt sensor. So usually you're often doing AO in infrared, but your sort of tip tilt guide star is often observed using an optical tip tilt sensor because it's easier to acquire. There's more optical stars. So now there's this new sensor called TRIC installed on Keck. And what it does is it does your infrared tip tilt sensing in the infrared. So basically what you're getting is a better comparison between your infrared and science image. So hopefully you're minimizing that error. And it's actually using this tip tilt sensor that I talked about earlier. The galactic center group can actually see diffraction rings around individual stars now. So it does really well. The drawback for now is that it adds 15 to 30 minutes of overhead, and it can randomly drop out sometimes in the middle of observations, and you have to restart that process of acquisition.
How long has it been on Sky for?
Since I started this process, so like middle of 2020.
Oh.
Yeah, but it's mostly been used by Galactic Center because they care about it the most. They're also like more invested in this. They also get like a lot more time than any other science program. So if you have 2 nights a year, you're not going to risk using Trek usually. So the way P3 and Prime fits into all this is everything I've talked about, this forward model, everything that goes into it is modular. So it has basically a telescope module, a wavefront sensor module, and everything can be swapped in and out of it. So every upgrade that's ongoing at Keck right now, you can basically take that hardware, plug in the new hardware, and then this code itself should work seamlessly. So it is actually set up to work with this entire upgrade. So once this upgrade is on Sky, and it is on Sky, I know the asterism's on Sky, I know the real-time controller's working, I know that the trick is working. We will need a whole bunch of new calibrations and a whole bunch of new data to test this, but it is set up to do that in future. That's about it. The Fourier modules, PSFs work well. Our reconstructed PSFs also work well, even though they're not as good as like your state-of-the-art extraction PSFs, but we know where the work needs to go. The good thing is they're set up to accommodate these hardware changes in terms of the code. It is also kind of set up for a machine learning approach, which is what people are trying to do with TipTop at LAM. The other thing I did not mention throughout was I talked about Keck, but this P3 prime architecture was actually developed for BLT. So this whole thing is set up so you can actually swap in like entire telescope and instrument systems in and out of this as well. So there's a NERC2 component which can become Sphere. There's a Keck component which can become BLT. So this whole thing is modular and can actually be adapted to different telescopes and instruments as well. Yeah, so that's the last slide, and I can take any questions now as well.
I think we can take some food first and we can discussion.
Okay. I don't know if people online have to leave or so I think everyone here will be used to, because I know there's a telecon as well.
Anyone have questions online? Looks like not. Let me check. Someone leave the message. Oh, we're unable to see the entire screen. Can we get it?
Oof.
I'm sorry because the speakers. Yeah, we faced some problem about Zoom. Yeah, that's also the reason why we start later today. I think I can send out.
I can send the slides.
Yeah.
To, yeah.
I can send out a slide to everyone.
Yeah, I'm sorry about Zoom. It has just stopped working and I'm not able to fix it.
If not, then everyone grab some food and we can discussion.
Yes.
Thank you.